Pluto is a distant and mysterious dwarf planet, a planet that once belonged to our solar system. Recent, unexpected announcements made by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the limelight with a startling discovery. They propose that this frigid world is on a possible path of collision with Neptune. But how could this occur, and what would be the repercussions of such a massive event? Are we witnessing a rare occurrence in astronomy, or is there something more to this looming threat? Join us as we explore the cosmic clash and the potential effects of Pluto and Neptune. Pluto was once classified as a planet but was later reclassified as a dwarf planet due to its peculiar orbit. Despite this, it remains a subject of intrigue and research in the astronomical community. According to recent forecasts by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku have raised the alarm about a possible perilous collision between these two celestial bodies, which could present a significant threat to Earth. How could such an event possibly occur? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes an incredible 248 years to complete one orbit, meaning that since its discovery in 1930, it has not yet completed a full revolution. But the fascination doesn't stop there. Pluto's high gravity influences its path, giving it an elliptical shape that deviates significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its steep inclination of 17 degrees to the ecliptic plane. This means Pluto's trajectory is much steeper than those of other planets, adding layers of complexity to its orbital pattern. One of the most fascinating features of Pluto's orbit is its interaction with Neptune's. For about 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This naturally leads to an important question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to comprehend its distinct path. Unlike other planets, which follow relatively predictable orbits along the ecliptic plane, Pluto's orbit stood out due to its steep slope and elliptical shape. The mystery deepened when scientists realized that Pluto's orbit technically intersects Neptune's. This raised concerns about the stability of both bodies. However, further analysis revealed that Pluto's orbit is stabilized by several gravitational mechanisms. One key factor is libration, a phenomenon in orbital mechanics. In the case of Pluto and Neptune, libration ensures that whenever Pluto enters Neptune's orbital path, it remains at least 90 degrees away from Neptune. This spatial separation prevents their paths from leading to a collision. Another important factor is latitude libration, which refers to the vertical movement of a celestial body in its orbit. Pluto's orbit places it significantly above Neptune's orbital plane when they are closest to each other. This additional separation further reduces the risk of collision. A third crucial component in this equation is the VZK oscillation, named after scientists von Zeipel, Kozai, and Lidov, who studied gravitational interactions in space. This oscillation explains how three celestial bodies, Pluto, Neptune, and the Sun, exert gravitational influences on each other. The VZK oscillation helps regulate Pluto's seemingly erratic path, maintaining its stability over long periods. Although Pluto's orbit appears chaotic, these stabilizing mechanisms ensure that it remains in a predictable trajectory. Numerical simulations in the late 1980s revealed that despite its chaotic nature, Pluto's orbit remains stable over incredibly long timescales, effectively keeping chaos at bay. Recent computer models have demonstrated that Pluto's stability is also influenced by Jupiter and Saturn. These massive planets exert gravitational forces that help keep Pluto on a secure orbital path. In particular, Jupiter's strong gravity plays a significant role in maintaining Pluto's stability for billions of years. This intricate gravitational dance among Neptune, Jupiter, and Saturn ensures that Pluto continues to move safely through space without veering into a collision course. Without such mechanisms, the solar system would be far more chaotic and unpredictable, with bodies like Pluto potentially colliding with others or being ejected from their orbits. For Pluto, particularly in light of discussions about a possible future collision with Neptune, understanding its orbit is essential. This knowledge provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how seemingly unstable orbits can achieve equilibrium through complex gravitational interactions. It also highlights the importance of continuous observation and study of celestial mechanics to better understand our place in the universe. Space exploration often leads us to confront the unpredictability of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which describes how even small variations in initial conditions can lead to significant changes over time, is vividly illustrated by Pluto. This means that even slight changes in Pluto's velocity or position could dramatically alter its long-term trajectory. Computer simulations have been invaluable in helping scientists understand how Pluto moves through space. By using advanced mathematical models, researchers can simulate the gravitational interactions between Pluto, Neptune, and other celestial bodies, refining our understanding of the forces that govern our solar system. Astronomers are able to see how even small alterations can have a big impact. Differences in Pluto's position when it returns to the same spot in its orbit reveal intriguing insights. These simulations, which began in the late 1980s, uncovered a fascinating fact about Pluto's path. Despite having stabilizing factors such as U and latitude libration, its orbit can still be quite wild and baffling. If you start with a minuscule difference in how fast Pluto is moving or where it is, its path may ultimately look very different. Even with all this chaos, Pluto's orbit remains stable for a very long time. Pluto has been around for billions of years, and its journey around the Sun, though seemingly chaotic, follows an underlying order. Predicting cosmic occurrences, particularly those involving erratic orbits like Pluto's, poses significant challenges. The inherent unpredictability of such systems means long-term forecasts are often uncertain. While numerical simulations provide effective methods for understanding and anticipating the paths of celestial bodies, they also highlight our predictive limitations. These models heavily rely on the accuracy of initial conditions and the intricate nature of the interactions they simulate. Any minor error or oversimplification can lead to vastly different outcomes, making precise predictions a difficult task. The chaotic nature of celestial orbits like Pluto's serves as a reminder of the ever-changing and dynamic nature of the universe. Pluto exemplifies how our understanding of space is still evolving. Studying the gravitational effects of enormous planets on Pluto provides valuable insights into the broader dynamics of the solar system. The presence and position of each planet influence the stability and trajectories of other celestial bodies. Recently, some astrophysicists have raised concerns about a possible collision between Pluto and Neptune. Despite these complex forces at play, Neptune's gravitational influence helps prevent such an event. Neil deGrasse Tyson, a prominent astrophysicist and science communicator, provides a unique perspective on these mysteries of the solar system. Best known for his role in Pluto's reclassification from a planet to a dwarf planet, Tyson offers insightful analysis on the changing nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in our ever-expanding knowledge of the solar system. He views this reclassification not as a demotion but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics emphasizes ongoing learning and adaptation. He sees the complexities of Pluto's orbit as a reminder of how much remains to be discovered. In light of these unknowns, Pluto's interactions with Neptune highlight the unpredictable nature of our solar system. Tyson emphasizes that the more we learn about space, the more questions arise, pushing us to explore further and deepen our comprehension of the universe. Michio Kaku, another well-known physicist and futurist, offers a complementary perspective on the mysteries of space. Kaku's expertise lies in bridging complex scientific concepts with futuristic visions, making him a key figure in discussions about celestial mechanics and broader astrophysical implications. Kaku's views on Pluto and its orbit emphasize the necessity of constant observation and advanced modeling to prepare for and understand potential cosmic events. He sees the interactions between celestial bodies as an important field of study, not just for academic curiosity but also for practical implications. The possibility of a Neptune-Pluto collision, while largely theoretical, exemplifies the dynamic and often chaotic nature of space. Kaku's futurist outlook urges us to consider the broader consequences of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His perspective highlights the importance of being prepared for the unexpected in space. He suggests that the more we understand these cosmic forces, the better equipped we will be to navigate and potentially mitigate their consequences. Both Tyson and Kaku agree that space is an endless frontier of discovery, and our current understanding, though vast, is still limited. Their emphasis on continuous exploration and sophisticated modeling reflects the evolving nature of space science. They stress the importance of not only understanding current celestial mechanics but also anticipating how they may change in the future. The potential for a future collision between Pluto and Neptune serves as an example of the larger challenges and opportunities in space exploration. It underscores the necessity of robust scientific inquiry, advanced technology, and the willingness to revise our understanding as new information emerges. Tyson and Kaku's exploration of space's mysteries, exemplified by Pluto's orbit, calls upon the scientific community and humanity at large to keep pushing the boundaries of our knowledge. The general scientific consensus is that, in the near future, Pluto and Neptune's orbits will remain stable due to their mean motion resonance and the various gravitational forces at play. A direct collision between them is highly unlikely. However, the complexities and potential perturbations in orbital dynamics mean astronomers must continue monitoring these celestial bodies to better understand their long-term behavior and any possible risks they may pose. While the scenario of a Pluto-Neptune collision is mostly speculative and considered unlikely, it highlights the importance of continuous research and astronomical observation. Advances in technology, such as more powerful telescopes and improved computer simulations, will help astronomers refine their models and predictions. This will ensure that we remain informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's focus on the unpredictable nature of celestial mechanics both emphasize the need for ongoing investigation and adaptability in our understanding of the universe. While the possibility of a Pluto-Neptune collision captures attention, it ultimately serves as a reminder of the complex and dynamic interactions that define our solar system. Through continuous research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-changing cosmos in motion.